So progress test E, the meaning of the term periodicity is the repeating pattern of physical and chemical properties. The key thing that is needed in here is the word repeating. Okay. B, an element in period 4 with the highest electronegativity value. So we need to go to our periodic table. And remember, period 1 starts here, 2, 3, 4. And we're looking on the far right-hand side here. So you could have bromine or krypton, although krypton being a noble gas, is why you're allowed either of those, really. So krypton or bromine. And identify the element in period 4 with the largest atomic radius. And again, with the periodic table, as you go across period 4, they get smaller. So the largest one is going to be potassium. So element potassium, and the reason for that is it has same number of shells, similar shielding, but it has the least number of protons, therefore weakest attraction, therefore largest radius. Okay, next one. So property of arsenic that describes what's happening here. Well, it's reacting with an acid and also a base, which means it's going to be amphoteric. And then complete the equation for the formation of arsenic hydride. So now what we need to do here is we need to break this down into its redox elements. Now the redox elements that we have in this is the hydrogen, so the hydrogen over here has a value of +1 and over here it is -1. We also need the zinc, so the zinc over here and the zinc in zinc nitrate. So it is 0 here and it is +2 there. Now, we need to make sure that the redox elements balance first of all, and they don't balance in this one here. So I need to have a 3 there. So I've got 3 1 pluses, which basically means the overall change, and I've got 3 1 minuses there, the overall change in the oxidation number of all of the hydrogens there is 6. So it's gone down by 6. And this one here has gone up by 2, which means I need to multiply everything here by 3. So if I put a 3 there and a 3 here. Now, normally at this point, we'd be balancing with our oxygens with water and our hydrogens with hydrogen ions. The thing is, we've got nitrates and nitric acids, so we're going to use those to kind of balance it up. So what I'm going to do is I'm going to combine it at this stage and then try and balance the rest of the elements using macho. So let's just put those together first of all. So we've got HNO3, 3 of those, with 3 zincs, which goes to ASH3 plus 3 zinc nitrates. I am missing the astatine, so I'm going to put that over here as well. So AS2O3, and I'm now going to do the kind of macho as we go down here. So the metals, well, the zinc's balance, that's fine. The astatines does not balance. I've got 2 over here, but I've only got 1 over there. So rather than halve this one, because I've got 3 oxygens in there, what I'm going to do is I'm going to double everything else up. So my 3 here is going to become a 6, 6, 2, and then a 6 there. So let's just tidy that up a little bit. Let's rewrite that out and then we'll go from there. So AS2O3 plus 6HNO3 plus 6ZN goes to 2ASH3 plus 6ZN NO3. Okay, so metals, let's check them again. So I've got 2 astatines on both sides, that's fine. I've got 6 zincs on both sides. If you remember, I was going to balance the nitrates with the nitric acids. So just really looking at the ends here. So over here, I've got 2 in zinc nitrate and 6 of those. So 2 6s are 12. So I've got 12 in there. And I've only got 6 in here. So what I'm going to do is I'm going to add another 6 nitric acids to that, which will make the nitrogens balance. Okay, so if I add another 6 to that, that will make that 12. So I've got 12 nitric acids over here. So that now gives me my 12 nitrogens. So the nitrogens balance, the metals balance. Let's check the oxygens. We're going to need water, so let's check the oxygens now. So 12, 24, 36, 37, 38. So I've got 39 on this side, and on the other side I've got 2 3s are 6, 6 6s are 36. So I need another 3 on this side, so I'm going to use water for that. So there's my 3 waters. So that gives me my 39 oxygens now. Just to check that off with my hydrogens, so 2 3s are 6, 2 3s are 6, so that's 12 hydrogens on that side, and I've got 12 hydrogens on this side as well, which means that this, with the water, is my balanced chemical equation. So when I transfer those over to the paper, that will give me 6, 12, 2, 6, and 3. Okay, next one. So magnesium, so let's just go to the periodic table. So magnesium is here. And if you remember, it is in the S block. So let's go back to this. So what block in the periodic table is it? It is in S block. You need to explain that. So it's highest energy electron is in an S orbital or subshell. Okay. So we've got an AR of that can consist of 3 isotopes. We've got 2 of the isotopes and the percentage abundance. So we're not sure what the mass is here. The mass is here of the other isotope. And the abundance, we can work out the abundance of the 3rd isotope. So total abundance is going to be 100%. So 100 minus 10 minus 78.99 is going to equal 11.01. So 11.01%. I've got to give my answer to 5 significant figures, and that's something I'm likely to forget. So before I do the calculation, I'm just going to write myself a little note down here that I've got to give my answer to 5 significant figures. And I now just work this out. So the relative atomic mass is 24.305. That is equal to 23.985 times 78.99 plus 24.986 times 10 plus 11.01 times m, all divided by 100. And when you work that out, you have a mass that is equal to 25.984. So 25.984. And that is to 5 significant figures. Okay. Next one. So C, we have calcium oxide added to water and then strontium oxide added to water. What do we know about these? Well, we know that the calcium hydroxide is sparingly soluble. So write an equation for calcium oxide with water. So calcium oxide and water is going to form calcium hydroxide, which is that, and that's all balanced. And then the pH of the calcium oxide, so it's going to be alkaline, which means its pH is going to be above 7. However, because calcium hydroxide is sparingly soluble, there will be less hydroxides in solution than strontium. Which means its pH, although it has to be above 7, it must be less than that of strontium. So I'm going to pick 9. And for strontium oxide, I'm going to pick 13. Okay. Number 3. Mechanism for this reaction. So CH3, C, HBr, and then Cn minus lone pair on the carbon. And I put my dipoles on, that always helps. D minus, D plus, because I know that electrons are going to be attracted to something that is slightly positive. And the carbon-bromine bond is going to break. And because the bromine is more electronegative, it's already pulling those pairs of electrons, or that pair of electrons, towards it anyway, so we're going to have that. So there's 1 mark for that arrow and 1 mark for that arrow. The IUPAC name of D, remember you've got to include the carbon in the CN, so it's going to be prop. And what is often missed out is the E, so it is going to be propane nitrile, and that E has to be there. Atom economy is the MR of the product, and the MR of the product is 55, divided by the mass of all of the products added together, so that's going to be 55 plus 119. It's a percentage, so I need to times it by 100, and if you work that out, you get 31.6%. Okay, next one. So what have we got? We've got a spirit burner. We've got 50 grams of water. It's cyclohexane. We're burning, which means it's going to be, here we go, the enthalpy of combustion is that, so it's going to be exothermic. I've got the specific heat capacity and I've got the MR, and the difference between these two values are going to allow me to work out the mass. Right, what am I asked to calculate? I need the final temperature of the water in this experiment. Okay, so let's start with the number of moles. Number of moles is going to be the mass, and the mass is going to be 192.730 minus 192.1, which is 0.630. Mass divided by the MR, which we're given, is 84. And that gives us 0.0075 moles. I need to work out the quantity of heat energy. Now, if you remember, delta H is Q over N. So Q is going to be delta H multiplied by the number of moles. And I've got delta H in the question, which is 1216. Now that's in kilojoules, and I need to convert that into joules because the quantity of heat in MC delta T is in joules. So I'm going to times that by 1,000, and then I need to multiply that by the number of moles, 0.0075. So the quantity of heat is 9120 joules. So we're now using Q equals MC delta T, rearranging that to get delta T. So delta T is Q divided by MC. So Q is 9120 divided by the mass. Now the mass, remember, in this is what your thermometer is sticking in, and it's sticking in 50 grams of water. So 50 times 4.18, which means the change in temperature is going to be 43.6. It's exothermic. And we started at 19.1 degrees. So the final temperature is going to be 19.1 plus 43.6, which is equal to 62.7 degrees C. Okay, so the Databook value for the enthalpy change of combustion is minus 3,920. The student concluded that the temperature rise recorded was smaller than it should have been. Why would that be? You've got a couple of things you can write here. So heat loss to the surroundings is always a good one. Or incomplete combustion. Okay, next one. So what are we working out here? So we've got the enthalpy changes of combustion, and we need to work out the enthalpy change for this reaction here. So we can do this in one of two ways. We can either do it using a Hess's cycle. Because it's combustion, we're burning all of these to give us our combustion products down here. So we're going to have 6 carbon dioxides, 6 waters, 6 waters in each case. So that will get you one of the marks. Alternatively, if you can't construct Hess's cycles, you can use the formula. So the enthalpy change is the enthalpy change of combustion, the sum of all of the enthalpy changes of combustion for the reactants minus the sum of the enthalpy changes of combustion of the products. They'll both give you the same answer. So that will be one of the marks. The next mark is for putting all of the values in. So 6 times minus 394 4 plus 6 times minus 286 minus 3920, which, so that would be your second mark. Third mark is for the enthalpy change, which is going to be minus 160 kilojoules per mole. Okay, so time of flight mass spectrometry. So how are these ionised in electrospray ionisation? 3 marks, so we need 3 things. So the sample will be dissolved. In a volatile solvent. It needs to be volatile so that it will evaporate. It's then passed through a hypodermic needle. With a positive charge. And what that does then, as the solvent evaporates, the molecule gains H+. So in here we're looking at the ion that reaches the detector first. It's going to be the one that's the lightest or the lowest MR or the smallest, which is this one. But what we've got to remember is that it has gained a proton, so it's going to be C3H5O2NH+. And now we're looking at electron impact. So for a germanium atom, so that's going to be GE plus E minus gives GE plus 2E minus. You can cancel one electron out, which will just give you this. Either are fine. Okay. So in the time of flight mass spec, we've got the time here. We've got the energy here. We've got the distance here, but that's in centimetres and it needs to be metres. Kinetic energy, that's in joules, and in this equation here that needs to be in kilojoules. No, ignore that. Use the information. What else have we got? So we've got Avogadro's constant. Use the information to calculate the mass in grams of 1 mole of these germanium atoms. So let's have a look. So we've got this here. So I need the mass from there. That's going to give me the mass of one of the ions. And once I've done that, I need to multiply it by this to get the mass of a mole of ions. I haven't got the velocity, but I can work that out using time and distance. So let's do that first. So velocity is distance divided by time. The distance is 0.96 meters divided by 4.654 times 10 to the minus 6, which is equal to 2.06274 meters per second. So now I can work out the mass by rearranging the equation. So the mass is 2 times the kinetic energy divided by the velocity squared. So 2 times kinetic energy is 2.438 times 10 to the minus 15, all divided by 20627 squared. So the mass there then is 1.146 times 10 to the minus 25 kilograms. Okay, so that's the mass of one iron. So the mass of a mole of ions is going to be 1.146 times 10 to the minus 25 times Avogadro's number, which is going to equal 0.06901. Remember, that's in kilograms. So to convert that into grams, that is going to be 69.01 grams. So the mass number of the iron is going to be 69. The mass of 1 mole of germanium ions is going to be 69.01 grams. Okay, good. We do need a whole number there because obviously in the mass spec they're whole atoms with whole protons and whole neutrons. That there's no kind of weighted average of the isotopes. Okay, next one, question number 6. So outline the mechanism. And this is with hydrogen bromide. And we need the major product. So let's start with our curly arrows. First of all, dipoles again always help. So D plus, D minus. So the D plus end of the molecule is attracted to the electron-rich carbon-carbon double bonds from the middle of there to the hydrogen. And then the hydrogen-bromine bond breaks, going to the bromine because that's the most electronegative, which is going to give us our carbocation. The question is, which is the correct carbocation? So the carbocation, the positive charge, is going to go on that carbon there because that's got the most number of alkyl groups attached to it. So that gives H3C, C, CH3, C, CHO, H, hydrogen is going on there, and my positive charge is going to go there, and my Br minus. Need my lone pair of electrons. Remember, the curly arrows have got to start from the pair of electrons, which goes to that positive carbon there, which then gives me my final product, that one there. Okay, so there'll be 1 mark for each correctly drawn curly arrow and 1 mark for the correct intermediate. Why do we get this one as the major product? So again, we've got to kind of look at what we would have here. So we need to talk about the major product forming, and this is where most people mess up. So the major product is formed from now we've got a tertiary carbocation here, tertiary carbocation. Let's just make sure we understand that that's tertiary. So I've got 1, 2, 3 on there. If it was on the other carbon, if the positive charge was here, for example, I'd have 1, 2. So that will be a secondary carbocation. So formed from the tertiary carbocation, which is more stable than a secondary carbocation due to the positive inductive effect. Or you could say that it has more alkyl groups attached. Okay, next part. So we've got two molecules here, geraniol and citronellal. These compounds can be distinguished by a simple test tube reaction. So we need to have a look at the functional groups. So let's just label those. So I've got an alkene there, alkene over here, and then I've got a primary alcohol there. I've got an aldehyde over here, and I've got an alkene there. The alkenes aren't going to be any help, but I do have a primary alcohol and an aldehyde, both of which can be oxidized, so dichromate isn't going to be any help here. So I need the test for an aldehyde, which is, it's the silver mirror test, so that's Tollens reagent. So with geraniol, so that's the primary alcohol, so there'll be no observable change. And with citronellal, we should see a silver precipitate. The molecular formula, it's just counting up the carbons, hydrogens and oxygens, is C10H18O. Why are they structural isomers? So this is the definition that we need to put down. So it has the same molecular formula, but a different structural formula. And then for stereoisomerism, we have the same, again, just another definition, same structural formula, with a different arrangement or 3D arrangement of atoms in space. Okay. We're now looking at the type of stereo in geraniol. So as they've got double bonds, I'm going to look for the geometric first, which is two different groups on each carbon of the carbon-carbon double bond. Well, that one's got the same group, that's methyls. This carbon here has a methyl there and the rest of it there, so that's a tick, that works. And then I've got a hydrogen here and the rest of that there. So, yep, that one's going to be geometric, or EZ. Explanation, so for each carbon, the carbon-carbon double bond, and I'm just going to put carbon 2 and carbon 3, have two different groups attached, and of course it's not just that, it's the carbon-carbon double bond doesn't allow free rotation. And then in citronella, so for exactly the same reason, it's not going to be geometric there, so I'm looking for something else, and I can see it here, carbon 3, I've got 1, 2, 3, and then I've got a hydrogen. That's 4 different groups attached. So that's going to be optical. 4 different groups. Attached to carbon 3. So draw a diagram to show 2 methanol molecules through hydrogen bonding, partial charges, lone pairs. Okay, so methanol, H3COH, and then okay, so at this point, just do a bit of an idiot check on yourself. I'm just going to see whether I've done that. So have I shown hydrogen bonding? Yes. Have I done 2 molecules? Yes. Have I got the partial charges? No. So I need to go back and put my partial charges on. So D minus, D plus, D minus, D plus. So now I can check those off. Lone pairs are all done. And something else that you need to be aware of is that this bit here needs to be at 180 degrees. If it is bent, V-shaped, non-linear, however you want to think about it, you wouldn't get one of those marks there. The OHO along there needs to be in a straight line. Okay. The next one. So the bond angle around the oxygen atom in methanol is slightly smaller than a regular tetrahedral. And we need to state why it is smaller. 1 mark, so it doesn't need a lot really. Lone pair electrons repel more than bonding pair of electrons. Okay, next part. Okay, so 6 marks here. This is going to be a levelled response question. So methanol is made by the reaction of carbon monoxide with hydrogen. So that's going to be an equilibria there. The reaction uses a copper-based catalyst. So I need to talk about a catalyst. Pressure of 10 megapascals. So I'm going to talk about pressure and temperature of 500 Kelvin. So each one of those, I reckon, is going to be worth 2 marks then. These conditions are used to provide a balance between, so I've got to talk about equilibria, which is the yield, the rate, and the cost. So yeah, here we go. So catalyst, pressure and temperature, yield, rate, and cost. Okay. So, I mean, the easiest way to do this is in a table, really. So, yield, rate, cost. Hopefully I won't run out of room. Okay, and we'll start by talking about a catalyst. So let's have a think about the catalyst. So catalyst doesn't shift the equilibria either way, so that has no effect. It increases the rate, which is good. And the cost, well, it's certainly lower than having a higher temperature, so it lowers the cost. There's one of them done, I reckon. So let's have a look at pressure. So that's that one done. Let's have a look at the pressure. So I've got 3 moles of gas on the right and 1 mole of gas. Sorry, 3 moles of gas on the left, 1 mole on the right. So pressure. So to get a high yield, I need a high pressure. Because obviously equilibria shifts to the side with fewer moles of gas. Increasing the pressure will increase the rate. And in terms of cost, high pressure has a high cost associated with it. And I reckon that's pressure done. So let's go with temperature. So it's exo in the forward direction, endo in the reverse direction. So let's go through each of these here. So in order to get a high yield, now it's an exothermic reaction, so I need a low temperature. So low temperature is required so that the equilibrium moves the forward or exothermic direction. I want a high temperature for the rate, to increase the rate, and high temperatures are costly. So for the temperature, it's probably somewhere in between. So the moderate temperature, 500 Kelvin is certainly moderate there. So moderate temperature. Okay, and that's probably got all 6 of the marks there, 2 for each basically, pressure, catalyst and temperature. Okay, and that is that. So somebody else will be doing the multiple choice. I hope that was okay, and see you soon.